Hi everybody, how's it going? So for my calculus project, I'm going to be finding the volume of a standing wavelength from a guitar string. So the theory behind it is that if you have a string fixed between two nodes, or fixed points that don't move, the string, after you apply an amount of tension to it, will oscillate back and forth between the two nodes. This oscillation will be reflected, and it gives this almost illusion that the string is standing still, which is why it's called a standing wave. So the equation that can be applied to a standing wavelength is represented by y is equal to 2a sine of kx cosine wt, which is a is the amplitude, the k is just 2 pi over the wavelength, and the omega is just 2 pi frequency, and t is just time. So the application of the calculus part is that we're going to be finding the volume of that equation. And finding the volume is important because you get to understand how the sound will sound. So if it's a smaller volume, smaller sound, larger displacement, so how much you pull the string will give you the volume. Alright, so in order to do this, we're going to have to find the measurements of the guitar string, or the string between two fixed notes. So for me, I'm going to be using my guitar. I'm going to be using the low E note, which is going to produce the lowest sound. So that low E note is, or the low E string, I mean, it came out to be about 12.75 inches, which rounds out to be about 0.3239 meters. And so for the frequency, it's going to be measured in hertz, and I'm going to use this online software right here. It's just an app on my phone. And so I took 3 measurements playing the low E note, and then after I took measurements of those 3, I took the average of it, which came out to be about 82.1 hertz. And so I found the accepted value online, which came out to be about 82.14 something hertz. And so finding the percent error, it came out to be about 0.38%, which is pretty accurate. And so for omega, using the frequency we just found, 82.1, we came out with omega being 162.2 pi. The wavelength, we're going to assume 4 overtones, so we're going to use this equation right here. And so the wavelength is 0.12 meters. K, which is just the wavelength we found right here under 2 pi, is just going to be 2 pi over the wavelength, 0.12. And time is just inverse frequency, 1 over frequency, which is 1 over 82.1. And so the amplitude, which is just the displacement. So if you have a wavelength going like that, the peak and low point is just how much you displace it, or how much you pull on the string. So we're just going to assume we displace it about 0.4 centimeters. Alright, so using all the numbers we just found, we're going to plug it into the equation, which gives this little monster right here. And so we're going to integrate it from 0 to 1884.9, which is going to be the 0, which if you look at the graph over here, it's going to be like that point. So the volume under the wave, just to reiterate, is important when you're working with music theory to understand how displacement affects the pitch and the sound of musical notes. And we're going to be evaluating the first harmonic between the first 2 notes. So if you look at the chart on the right hand side, we're going to see that the smaller the displacement, it's going to be quieter, which is what you should expect. If you don't pull on the string too much, it's not going to produce as loud of a noise. And if you pull the string a lot, you're going to see that the volume is going to be a lot louder. And when I say volume, I mean in decibels. And so finding that, which is going to be the integral, not the area, but we're going to use some method. And then it shows the pitches right here. So we're going to use the first harmonic. And so using this equation right here, it looks really messy, but it's really not that bad. So we're just going to have, we're going to use the disk method. And so we just pull out the pi constant, square the equation, and this big mess right here is just a constant. We could pull that out as well, do a simple u sub, change the constant of integration, pull out that new constant we have. And then we're going to integrate that sine squared of u, plug in the constants, and then we're just going to simplify it. That's all it is. It's just going to be a really ugly number, which is this right here. That's the exact value except for the approximation we did earlier. But when we round that out, it's going to come out to be 18.4 times 10 to the negative 6 meters cubed. And it's a very small value, which is what we should expect, considering that the low E note is the lowest note. Alright, so in conclusion, even though this calculus application is not very useful, because finding the sound isn't very beneficial, because there's a lot of things that affect how a string will sound, including the material, weight, density, etc. But it is a good tool to predict how it should sound. And thank you so much for watching. And that's my works cited.